Our universe is a place of constant motion. Galaxies swirl through the vastness of space. Stars are born, live, and die in fiery explosions. Planets orbit their stars, their surfaces ever-changing. But where did all this motion, all this energy come from? The answer, scientists believe, lies in an event that happened billions of years ago, the Big Bang. The Big Bang Theory is our best explanation for the origin of the universe. It suggests that everything we see around us, from the smallest atom to the largest galaxy, was once concentrated into a single, incredibly hot and dense point. This point, smaller than an atom, contained the seeds of everything that would become the universe. Then, about 13.8 billion years ago, this point began to expand. This wasn't an explosion in the traditional sense, like a bomb going off in space. Instead, it was the expansion of space itself, stretching out in all directions at an incredible speed. As space expanded, it cooled, and the energy that was once concentrated in that single point began to transform. The Big Bang wasn't just the start of our universe, it was the start of time itself. Everything we know, the laws of physics, the fundamental forces of nature, all came into existence in that first moment of cosmic expansion. Understanding the Big Bang is therefore key to understanding not just where we came from, but also what our universe is made of and how it works. The idea of the Big Bang might seem strange, even unbelievable. How can we possibly know what happened billions of years ago at the very beginning of time? The answer is that the Big Bang left behind clues, echoes of that ancient event that we can still detect today. One of the most important pieces of evidence for the Big Bang is something called the Cosmic Microwave Background Radiation, or CMB for short. This is a faint afterglow of heat and light left over from the Big Bang. It's like the faint heat you feel on a brick wall long after the sun is set. This radiation fills the entire universe and is remarkably uniform, indicating that it originated from a single, incredibly hot event. Another key piece of evidence comes from the way galaxies are moving. Scientists have observed that galaxies are moving away from us, and the farther away a galaxy is, the faster it's moving. This observation, known as redshift, is exactly what we would expect to see if the universe were expanding outwards from a single point, just as the Big Bang Theory predicts. These observations, along with many others, provide strong support for the Big Bang Theory. While there are still some unanswered questions, the evidence overwhelmingly suggests that our universe did indeed originate from a single, hot, dense state billions of years ago. The Big Bang wasn't a single event, but rather a process that unfolded over time. In the first fractions of a second after the Big Bang, the universe was a place of unimaginable heat and energy. It was so hot and dense that the fundamental forces of nature, such as gravity and electromagnetism, were unified into a single force. One of the key events in this early universe was the Planck epoch. This period, named after the incredibly small Planck scale, lasted for just 10 to the power of minus 43 seconds after the Big Bang. During this time, the universe was so small and dense that our current understanding of physics breaks down. We need a theory of quantum gravity, something that combines Einstein's theory of gravity with the principles of quantum mechanics to understand what happened during this epoch. As the universe expanded and cooled slightly, it entered the inflationary period. During this period, which lasted for a tiny fraction of a second, the universe underwent an exponential expansion, increasing in size by a factor of at least 10 to the power of 26. This rapid expansion helps to explain why the universe is so uniform on large scales and why the CMB is so evenly distributed. The inflationary period is a crucial part of the Big Bang Theory, but it's also one of the most mysterious. We don't yet fully understand what caused this rapid expansion or how it ended. However, scientists are actively researching this period using observations of the CMB and other cosmic phenomena to try and piece together the details of this early chapter in the universe's history. The building blocks of everything. As the universe continued to expand and cool, the energy that was once dominant began to condense into matter. This process, known as baryogenesis, is one of the most important events in the early universe, as it led to the creation of the protons, neutrons, and electrons that make up everything we see around us. Initially, the universe was a sea of elementary particles, including quarks, leptons, and their antiparticle counterparts. As the universe cooled, quarks combined to form protons and neutrons, the building blocks of atomic nuclei. Electrons, which are leptons, remained free-floating. However, the early universe was a violent place, with particles and antiparticles constantly colliding and annihilating each other. For reasons that are still not fully understood, a slight asymmetry between matter and antimatter arose, with slightly more matter being created than antimatter. This tiny imbalance, perhaps just one extra particle of matter for every billion pairs of matter and antimatter, had profound consequences. As the universe continued to cool, all the antimatter annihilated with almost all of the matter, leaving behind a small surplus of matter. This leftover matter is what makes up everything we see in the universe today, from the stars and galaxies to planets and people. How did we go from gas clouds to galaxies? After the initial flurry of particle creation and annihilation, the universe entered a period of relative calm. The universe was now filled with a hot, dense soup of protons, neutrons, electrons, and photons. Over millions of years, gravity began to exert its influence, pulling these particles together into clumps and clusters. The first structures to form were vast clouds of hydrogen and helium gas. These clouds, drawn together by gravity, began to collapse in on themselves. As they collapsed, they heated up, and eventually the pressure and temperature at their cores became so intense that nuclear fusion ignited, marking the birth of the first stars. These early stars were much larger and hotter than our sun, and they lived fast and died young, exploding as supernovae after just a few million years. These explosions scattered heavy elements, cooked up in the cores of these stars, throughout the surrounding space. These elements would later go on to form planets, moons, and even life itself. Gravity continued to shape the universe, pulling together clusters of stars to form galaxies. Our own galaxy, the Milky Way, formed around this time, a vast spiral of billions of stars slowly rotating around a central supermassive black hole. A universe of light and shadow. As astronomers peer deep into the cosmos, they've discovered that the universe is not just filled with stars and galaxies, but also with vast regions of darkness. These dark regions are not simply empty space, but are thought to be filled with mysterious substances known as dark matter and dark energy. Dark matter doesn't interact with light, hence its name, but its gravitational influence can be seen in the way galaxies rotate and cluster together. Scientists estimate that dark matter makes up about 85% of the total matter in the universe, even though we can't see it directly. Dark energy is even more mysterious. It's thought to be a form of energy inherent to the fabric of space-time itself, and it's causing the expansion of the universe to accelerate. This accelerating expansion was a surprising discovery, and scientists are still trying to understand what dark energy is and how it works. The study of dark matter and dark energy is one of the most exciting and challenging areas of modern cosmology. Unveiling the secrets of these mysterious substances could revolutionize our understanding of the universe and its ultimate fate. The quest for understanding. As our journey through the cosmos continues, we find ourselves at the forefront of one of humanity's greatest quests, to understand the true nature of the universe. Scientists around the world are constructing enormous telescopes, launching sophisticated satellites, and developing new technologies to peer deeper into space and time than ever before. These efforts are not just about observing the distant stars and galaxies, but also about probing the very fabric of reality itself. One of the most ambitious projects is the James Webb Space Telescope. With its advanced infrared capabilities, it aims to explore the universe's earliest galaxies, study the atmospheres of exoplanets, and uncover the mysteries of dark matter and dark energy. Meanwhile, particle physicists are using powerful accelerators like the Large Hadron Collider to recreate conditions just moments after the Big Bang, hoping to discover new particles and forces that could explain the fundamental workings of the universe. The universe is vast and complex, and each new discovery often raises more questions than it answers. If you like these videos and want to learn more about your infinite universe, like and subscribe to the channel.